A vast cloud of cosmic gas glows with the light of newborn stars. This is the Orion Nebula, a stellar nursery just over 1,300 light-years away. But behind its famous beauty lies a universe of bizarre and violent activity. We are embarking on a journey to uncover 50 of its strangest secrets. You will discover cosmic bullets fired at supersonic speeds, natural lasers hidden in the dust, and stellar runaways ejected from a chaotic dance of gravity. We will investigate what triggers these colossal explosions of creation and whether the harsh environment could forge the very ingredients for life. What do you think is the most profound mystery waiting inside a nebula? Our first stop is a seemingly simple wall of gas and dust slicing across the nebula's glowing heart. Astronomers call it the Orion Bar, and it is far more than a scenic feature. This dense, sharp-edged ridge is a cosmic frontier, a battle line drawn between two titanic forces. On one side, the blistering ultraviolet radiation from the young, massive stars of the Trapezium Cluster. On the other, the cold, dark molecular cloud from which the nebula itself was born. The intense starlight is slowly eating away at the bar, evaporating it atom by atom in a process called photodissociation. This creates a visible boundary so crisp it looks almost artificial, a stark division between the bright ionized gas of the nebula and the shadowy material behind it. But within that eroding wall, something incredible is happening. The bar's unique environment, with its extreme gradients of temperature and pressure, acts as a vast natural chemistry set. Here, simple molecules shattered by the starlight can recombine into more complex forms in the slightly cooler, denser layers just behind the ionization front. It has become one of the most important laboratories in our galaxy for understanding how the building blocks of life, like water and even organic molecules, can form in the harsh emptiness of space. This one structure alone teaches us that creation and destruction are two sides of the same cosmic coin. That eroding wall of the Orion Bar is under constant assault from the nebula's central engine. At the very heart of this chaos burns the Trapezium Cluster, a tight knot of 4 brilliant stars you could theoretically cup in your hands if you were close enough. These are not gentle suns like our own. Theta 1 Orionis A, B, C, and D are stellar titans, each many times more massive and millions of times brighter. They are cosmic newborns, only about 1 million years old, yet they dominate their surroundings with a ferocious energy. Their primary weapon is the same ultraviolet light that defines the bar, but they wield another, more physical force just as powerfully. Stellar winds, these are not gentle breezes. Imagine the sun's solar wind, but amplified to a truly apocalyptic scale. From the surfaces of these massive stars, supersonic rivers of charged particles scream outward at speeds exceeding 1,000 kilometers per second. This relentless gale carves into the surrounding cloud of gas and dust like a celestial sandblaster. The result is the vast cavity we see at the nebula's center, a hollowed-out region where the trapezium stars sit in a relative clearing, having blown away the very material that birthed them. But this destruction is curiously creative. Where those powerful winds slam into the denser, colder gas at the cavity's edges, they compress it. They pile up material into new, dense walls. And inside those pressurized walls, gravity finds an easier foothold. The shock waves from the winds can trigger the collapse of pockets of gas, seeding the next generation of stars. So these 4 brilliant siblings are not just illuminating the nursery, they are actively remodeling it, using hurricane-force winds to both clear space around themselves and to build new stellar cradles in the suburbs of their domain. The sculpting winds from the trapezium stars do more than just shape the nebula's grand architecture. They reveal the fragile beginnings of entire solar systems. Scattered throughout the cavity, especially near its bright edges, are some of the most precious objects ever photographed in space. Astronomers call them proplyds, short for protoplanetary disks. In essence, each one is a newborn star swaddled in a thick, spinning pancake of gas and dust. This is the raw material for planets, the very stuff that coalesced into our own Earth and its siblings 4.5 billion years ago. What makes the Orion proplyds so spectacularly strange is their visibility and their peril. The Hubble Space Telescope captured them not as vague blobs but as distinct, sculpted forms. Many appear as luminous tadpoles frozen in the cosmic current. Their rounded heads are the disks themselves, glowing in the intense starlight, while streaming away from the trapezium is a long, comet-like tail. This tail is not a sign of growth but of evaporation. It is the disk's material being violently stripped away by the same stellar radiation that makes it visible. This creates a breathtaking and brutal paradox. We are witnessing the cradle of planet formation, but it sits inside a furnace. For any planets to form within these disks, the process must be a frantic race against time. The dust grains must collide, stick together, and grow into pebbles, then rocks, then planetary cores, all before the central star's fierce siblings blow the entire disk away into the void. Some of these infant systems may win the race, giving birth to new worlds. Others will be stripped bare, leaving behind a naked star with no planets to call its own. It is a stark reminder that cosmic birth is often a story of survival. While some disks are slowly evaporating, other structures in the nebula are born from a far more violent kind of eruption. Deep within the cloud, the Hubble telescope revealed a series of bizarre, fast-moving objects that look like they were fired from a cosmic cannon. Astronomers named them the Orion bullets. Each one is a compact, bullet-shaped clump of iron and neon gas, glowing with a distinct hue, and each is rocketing through the surrounding hydrogen cloud at speeds exceeding 400 kilometers per second. That is over 1 million miles per hour. To put that in perspective, a projectile moving that fast could travel from Earth to the Moon in about 16 minutes. As these superheated bullets tear through the colder, stationary nebula gas, they do not slip through quietly. They plow into it, creating brilliant, cone-shaped shockwaves ahead of them that we see as glowing blue bows. These bow shocks are like the V-shaped waves at the front of a speedboat, but forged in a furnace of colliding gases. They are the unmistakable sign of a supersonic object punching through a medium, and they tell us these bullets are not drifting. They are being violently propelled. So what cosmic event could possibly launch such strange ammunition? The leading theory points to a cataclysm hidden deep within the dusty core of the nebula, out of our direct sight. One possibility is that a massive star, much larger than those in the trapezium, reached the end of its life and exploded as a supernova. The shock wave from that titanic blast could have ripped through the cloud, compressing fragments of gas into these dense, molten bullets and hurling them outward. Another idea suggests an equally dramatic but slightly different origin. Perhaps two or more very young, massive stars in a tight orbit had a gravitational clash so violent it resulted in a merger or a catastrophic explosion, ejecting jets of enriched material at incredible speeds. The presence of iron in the bullets is a crucial clue. Iron is forged in the hearts of the most massive stars and is often scattered into space by supernova. Its detection here suggests these bullets are not just simple knots of nebula gas. They are shrapnel from a stellar-scale catastrophe, possibly the first tangible evidence of a hidden, recent death at the heart of a famous stellar nursery. This means the Orion Nebula is not just a place of serene birth. It is also a graveyard, and the ghosts of its dead stars may still be screaming through the halls. The violence that forged the Orion bullets hints at even more colossal objects hidden from our direct sight. Deeper still, beyond the reach of even the Hubble telescope's penetrating gaze, lies one of the nebula's greatest enigmas. It is known as the Becklen-Neugebauer object, a name that sounds more like a secretive government project than a star. Discovered in the 1960s by its intense infrared glow, this object is completely invisible in ordinary light. The reason is a shroud of dust so thick and dense it could blot out 1,000 suns. This is not a gentle veil. It is a suffocating, opaque cocoon, a blanket of cosmic soot and ice hundreds of times thicker than our entire solar system. Within this near-total darkness, something monstrous is taking shape. The Nebula object is a protostar, a stellar embryo in its absolute earliest and most violent phase of formation. It represents a stage of life far more primitive than the brilliant, exposed stars of the Trapezium Cluster. While those stars have already cleared their birth clouds and shine openly, this object is still actively feeding, still gathering mass from its surrounding envelope in a chaotic, collapsing frenzy. The energy from this incredible infall of material cannot escape as visible light. Instead, it heats the immense cocoon of dust around it, causing that dust to glow with a deep, warm heat that we detect as infrared radiation. Think of it as seeing the heat signature of a forge through a brick wall. You cannot see the flames or the molten metal inside, but you can feel the intense warmth radiating through. That is how we know this object is there. Current estimates suggest it is a true behemoth, perhaps 15 to 20 times the mass of our Sun. It is a star in the making, so young that nuclear fusion may have only just begun to sputter to life in its core, fighting against the ongoing collapse. This hidden giant forces us to reconsider the nebula's timeline. The brilliant stars we see lighting up the gas clouds are not the first generation, they are the older siblings. The Nebula object is a member of a younger, still-forming family buried in the nursery's deepest, darkest recesses, reminding us that the most dramatic acts of stellar birth are often performed behind the curtain. Buried even deeper than the Nebula object lies the true powerhouse of the Orion complex. This is the Kleinman-Low Nebula, a name known not for its visual beauty but for its raw, churning power. If the trapezium stars are the brilliant chandeliers in the nursery's main hall, then Kleinman-Low is the roaring, hidden furnace in the basement. It is the engine room of the entire Orion Nebula. Seen in visible light, this region is a mere smudge of darkness, an impenetrable knot of dust. But switch the view to infrared, and the scene transforms into a blistering cosmic forge. Here, the star formation is not just happening, it is happening on an industrial scale. This dense core is a hotbed of massive stellar birth, a place where gravity's grip is so fierce it pulls together the material for stars many times heavier than our Sun. The activity is frantic and violent. From these deeply embedded protostars, astronomers detect powerful bipolar outflows, colossal jets of gas fired in opposite directions at hundreds of kilometers per second. These jets act like cosmic blowtorches, carving vast cavities through the surrounding cloud and releasing tremendous energy. Even stranger, the Kleinman-Low region crackles with natural laser emissions called masers. These are not the colorful beams of science fiction, but intense, focused radio waves emitted by molecules like water and silicon monoxide that have been energized by the violent conditions. Detecting a maser is like hearing a precise, screaming whistle over the general roar of the nebula, a clear signal of extreme turbulence and intense heat localized around a newborn star. This hidden engine room reveals a fundamental truth. The serene glow of the Orion Nebula that we admire is merely the peaceful facade. The real work of building the most massive stars, the true violence of gravitational collapse and magnetic fury, happens in these shadowy, infrared bright cores where light itself is trapped and energy escapes only as heat and radio whispers. The furious jets erupting from hidden protostars in Kleinman-Low do not simply vanish into the void. They announce their presence with brilliant, ephemeral beacons known as Herbig-Haro objects. These are not stars, nor are they simple clouds. They are cosmic shock fronts, the glowing aftermath of a violent collision. Picture a fire hose of supersonic gas blasted from the poles of a newborn star, plowing directly into a stationary wall of cold nebula material. The impact is catastrophic for the gas molecules involved. heating them to thousands of degrees and causing them to fluoresce with an eerie, structured glow. The result is often a pair of matching knots or bow-shaped clumps of light, positioned on opposite sides of the hidden protostar that created them. In the Orion complex, some of the most famous examples are Herbig-Haro 1 and Herbig-Haro 2. Though not located in the main nebula itself, they are part of the same vast star-forming complex, acting as perfect textbook illustrations. Hubble images show HH1 and HH2 as two bright, chaotic clouds facing each other across a dark divide. That dark center is where the invisible protostar lies, its twin jets punching out in opposite directions and lighting up the interstellar gas at the points of impact. These objects are more than just beautiful accidents. They are vital signposts for astronomers because they mark the precise endpoints of these stellar jets. They reveal the otherwise hidden location and orientation of the infant star. By measuring how these shock fronts move over time, scientists can clock the astonishing speed of the jets, often hundreds of kilometers per second, and even trace changes in the outflow's direction, hinting at the dynamic, wobbling environment right at the base of the star's formation. Each Herbig-Haro object is a temporary flare in the darkness, a brief cosmic signature written in shocked gas that tells us, here, right now, a star is fighting its way into existence. That hidden furnace of Kleinman-Low is not an isolated anomaly. It is merely the brightest, hottest knot within a far vaster and colder structure. To understand the true source of the nebula's splendor, we must pull our view back to see the immense, dark foundation upon which everything is built. This is the Orion Molecular Cloud 1, often abbreviated by astronomers as OMC1. It is the primary reservoir, the cosmic lumberyard that supplies all the raw material for this stellar construction site. While the nebula itself is the brilliant, ionized surface of the cloud, OMC1 is the deep, cold interior. Temperatures here can plunge to just a few tens of degrees above absolute zero. This profound cold is not a sign of emptiness but of incredible density. The gas here, primarily molecular hydrogen, is packed so tightly that it blocks all visible light, creating the dark lanes and shadows we see silhouetted against the nebula's glow. But peer into it with radio and infrared telescopes, and this seeming void comes alive with intricate structure. It is not a uniform blob. Instead, it is a tangled, filamentary maze. Giant strands of cold gas and dust, each light years long and woven through with magnetic fields, crisscross the cloud like the threads of a colossal cosmic spiderweb. These filaments are the fundamental architecture of star formation. Gravity works most efficiently along these dense ropes, pulling material into ever tighter knots. Where several filaments intersect, the density soars, creating the perfect seeds for future stars. The Trapezium Cluster, the Beckmann-Neugebauer object, and the Fury of Kleinman-Low all owe their existence to this slow, gravitational collapse occurring within the web of OMC1. The nebula's fireworks are just the final, bright flash of a process that began in near-total darkness and profound cold. A reminder that the most spectacular cosmic events are born from the quiet, patient gathering of material over millions of years. Yet for all the furious activity in OMC1, it is not the only game in town. Just to its north lies a quieter but no less important sibling. Astronomers know it as the Orion Molecular Cloud 2 core. If OMC1 is the chaotic, brilliant main stage of the Orion complex, then OMC2 is the more subdued rehearsal hall next door. It is a region of slightly lower mass and somewhat less intense star formation, but this relative calm makes it an invaluable laboratory. Here, the processes are easier to observe without being completely overwhelmed by the glare and violence of its famous neighbor. The dust in OMC2 is a particular focus of study. Dust grains, tiny particles of carbon and silicate smaller than a speck of smoke, may seem insignificant, but they are the architects of starlight's appearance. They absorb the harsh ultraviolet radiation from young stars and re-emit it as a gentle, warm infrared glow. By meticulously mapping this infrared emission, astronomers can peer past the dust to census the population of young stellar objects hidden within. They find not the explosive birth of massive trapezium-like stars, but a more representative sample of stellar infancy. Dozens of low and medium-mass protostars and pre-main sequence stars are embedded here, each at a slightly different stage of development. Some are still deeply shrouded, accreting mass from thick envelopes. Others have cleared their immediate surroundings, their protoplanetary disks now visible. Studying this quieter core allows scientists to answer fundamental questions. How does the initial distribution of mass in a cloud affect the types of stars that form? What is the typical timeline for a sun-like star to emerge from its cocoon? In the comparative piece of OMC2, the universal rules of star formation can be read more clearly, free from the dazzling fireworks next door. It proves that for every spectacular stellar breakout, there are countless quieter births proceeding in the shadows. But this cosmic tapestry holds a secret about our own perspective. The three stars that form the iconic sword hanging from Orion's belt present one of the sky's most beautiful deceptions. To the naked eye, they appear as a neat celestial dagger, with the middle star noticeably fuzzy. That fuzziness is, of course, the Great Orion Nebula. It seems perfectly logical that these 3 points of light are siblings, embedded within the glowing cloud, all part of the same celestial structure. The reality, however, is a masterclass in cosmic alignment and sheer chance. These stars are not a family. They are strangers passing in the night, positioned at vastly different distances from Earth, and we are looking at them in a perfect straight line. The lowest star in the sword, known as Iota Orionis, is a brilliant blue giant located over 1,300 light-years away. The top star, Theta Orionis, is part of the Trapezium Cluster and sits directly within the nebula, also at that same approximate distance. But the middle star, the one that seems to pierce the heart of the nebula itself, is named Mintaka C. It is a foreground star, a much closer neighbor only about 200 light-years away. From our vantage point on Earth, Mintaka C aligns precisely between us and the nebula, appearing to be nestled within it. The nebula acts as a brilliant, glowing backdrop, a luminous screen against which this foreground star is silhouetted. This simple alignment creates the illusion of a unified sword. It reminds us that the sky is a two-dimensional canvas, and the depth we perceive is often an assumption. The universe is a master of illusion, arranging its wonders in lines of sight that can tell a story of connection where none truly exists. That perfect alignment of the sword stars creates a fixed landmark in our sky, but the nebula itself has a reputation for being anything but fixed. For centuries, astronomers gazing at the Great Orion Nebula have whispered about a strange and unsettling possibility. What if it is alive? What if it changes before our very eyes? This is the mystery of its historical variability. In the late 1600s, the famed astronomer Christian Huygens described the nebula as having a bright triangular core. Just a few decades later, other observers like Jean-Dominique Cassini sketched it with a noticeably different shape, some even reporting it had multiple centers of light. The most dramatic claim came from the astronomer William Herschel in the late 1700s. After years of observation, he became convinced the nebula's structure was undergoing real physical transformation. He speculated that he was witnessing the chaotic, ongoing process of star formation itself, a nebula condensing into new solar systems. For over 100 years, this idea captivated the scientific imagination. Was the Orion Nebula a dynamic, evolving entity, or were these observers simply seeing different versions of the same static truth? Modern astronomy has unraveled this puzzle, and the answer is a fascinating blend of both cosmic reality and human limitation. The primary driver of the perceived change was not the nebula, but the eye looking at it. early telescopes were small, with lenses that produced significant optical flaws. Different observers used different instruments with varying apertures and magnifications. A smaller telescope might only resolve the nebula's brightest, most compact core, making it appear star-like or triangular. A slightly better instrument would reveal the fainter outer loops and filaments, completely altering its perceived shape. Furthermore, the human eye is not a perfect detector, especially under the strain of peering into a dim eyepiece on a cold night. Contrast, fatigue, and even the observer's own expectations could dramatically influence what they recorded in their logbooks. So, much of the historical variability was an illusion, a story written by the evolving technology of perception. Yet there is a kernel of cosmic truth buried within the confusion. The nebula is illuminated by variable stars, particularly in the Trapezium Cluster. These young, massive stars are prone to violent flares and shifts in brightness. If the star Defy to 1 Orionis C, the primary ultraviolet engine of the nebula, were to brighten or dim even slightly, it would directly affect how brightly the surrounding gases fluoresce. A change in the lighthouse would change the glow on the fog. Modern photometric studies have confirmed small, subtle fluctuations in the nebula's brightness over years and decades, likely tied to these stellar personalities. So Herschel was not entirely wrong. He was just witnessing a far more subtle dance than he could have imagined, a dance where the slow improvement of human vision and the faint flicker of distant stars became forever intertwined in the historical record. The faint, cold dust of the Orion molecular cloud holds a secret signal, one that hums on a frequency we can barely perceive. Across the vast expanse of the nebula and its dark foundations, astronomers detect a persistent, anomalous microwave emission. This is not the familiar warmth of infrared, nor the sharp radio whistle of a maser. It is a diffuse, crackling glow that blankets the region, and its source is one of the most peculiar ideas in modern astrophysics. It appears to come from dust, but not the kind you might picture. The leading theory points to nanoparticles, tiny carbon-based molecules smaller than a virus spinning at unimaginable speeds. Imagine a grain of cosmic soot, a fragment of a larger dust particle that has been shattered by ultraviolet radiation or shock waves. These nanofragments are not stationary. They are thought to become electrically charged, and when placed in the weak magnetic fields that thread the interstellar medium, they begin to spin. And not just a slow rotation, but a frantic billion times per second whirl. This hyperrotation causes them to emit radiation at microwave frequencies, producing the faint, widespread glow that telescopes like Planck have mapped across Orion. This phenomenon is a profound puzzle because it does not behave like normal thermal radiation. If you heat a dust grain, it glows in infrared, a predictable, broad spectrum of light based purely on its temperature. This microwave emission is different. It is a specific, non-thermal signal, meaning its energy comes from motion and interaction with magnetic fields, not just heat. Its very existence challenges our catalogue of what interstellar dust is made of and how it behaves. For decades, dust was considered a passive ingredient, something that simply blocks and reddens light. The discovery of this spinning nanodust reveals it as an active, dynamic component of the cosmos. These frenzied specks are more than just dirt. They are minuscule power plants converting rotational energy into a faint radio whisper, painting the cold clouds of Orion with a signature of perpetual, invisible motion. While the spinning nanodust whispers in microwaves, other structures in the nebula scream their history in visible light. Erupting from the hidden furnace of the Kleinman Low Nebula is a bizarre and intricate formation known as the Orion Fingers. In Hubble images, they appear as a series of elongated, comet-shaped knots, all pointing directly away from a central point like the petals of a fiery, cosmic dandelion that has been blown apart. There are dozens of these fingers, each one a clump of hydrogen gas glowing a vivid red, and they are all moving outward at staggering speeds. We are not talking about a gentle drift. These structures are racing away from their origin at velocities exceeding 400 kilometers per second. They are not being gently pushed by stellar winds. They appear to have been violently ejected all at once in a single catastrophic event. The geometry tells a clear story. If you trace the paths of all these fingers backward, they converge on a specific location deep within the dusty heart of Kleinman Low. This is the epicenter, the ground zero of what must have been a titanic explosion. The leading hypothesis for what caused this event is as dramatic as the fingers themselves. Astronomers suspect that several hundred years ago, perhaps around the time Galileo first turned his telescope to the heavens, a gravitational catastrophe unfolded in that hidden core. Two or more incredibly massive protostars, each still forming and swaddled in immense disks of gas, may have been locked in a dangerously tight orbit. In such a chaotic, dense environment, their dance could have become unstable. They may have spiraled inward and violently merged, or one may have been gravitationally slingshotted away as a runaway star while the other received a tremendous kick. The energy released in such a merger or close encounter would have been unimaginable, equivalent to the simultaneous detonation of millions of nuclear bombs. That sudden, directional blast of energy would have punched through the surrounding molecular cloud, carving out tunnels of hot gas and dragging cooler material along with it. What we see today as the delicate, finger-like projections are the surviving shrapnel from that detonation, the leading edges of those blast waves where the ejected material is plowing into the surrounding nebula and lighting up. They are the lingering smoke trails of a stellar-scale bomb, frozen in their outward flight for our telescopes to decipher centuries after the echo of the explosion first rang out. The explosive fury that carved the Orion fingers also leaves behind a far more subtle, yet equally precise, signature in the darkness. Deep within those same dense cores where new stars are fighting to be born, space itself begins to act like a natural amplifier. This is the phenomenon of cosmic masers. The word maser stands for microwave amplification by stimulated emission of radiation. It is the microwave cousin of the more familiar laser, which uses light. In the cold, turbulent gas clouds of Orion, particularly around the Kleinman Low region, specific molecules like water and methanol become the key players. Under normal conditions, these molecules float quietly, absorbing and emitting tiny, random amounts of energy. But in the extreme environment near a newborn protostar, everything changes. The fierce radiation and powerful shock waves from the infant star pump enormous amounts of energy into the surrounding cloud. This energy excites the water and methanol molecules, boosting their internal energy to a much higher state. Think of it like winding up 1,000 tiny springs all at once. Now, here is where the cosmic magic happens. When a single, stray microwave photon of exactly the right frequency happens to pass by one of these wound-up molecules, it can trigger a chain reaction. The excited molecule releases its stored energy, emitting a new photon that is an exact copy of the first. Same frequency, same direction, same phase. This new photon then goes on to stimulate another excited molecule, and then another, creating a cascading, amplified beam of pure, coherent microwave radiation. The result is not a visible beam of light, but an intensely bright pinpoint spot on a radio telescope's map. These maser spots are millions of times brighter than the normal microwave glow of the cloud. They act like brilliant, natural lighthouses shining from within the deepest fog. For astronomers, they are invaluable tools. Because they originate from such small, specific regions around a protostar, they provide incredibly precise markers. By tracking the motion and velocity of these maser spots over time, scientists can map the otherwise invisible whirlpools and outflows of gas swirling around a star in its earliest moments. A water maser might trace a high-speed jet, while a methanol maser could map the slower, rotating disk of material feeding the star. They allow us to take the pulse of stellar birth in places our optical telescopes can never see, turning the chaotic noise of a molecular cloud into a clear, amplified signal of creation. That amplified microwave whisper from cosmic masers points directly toward the nebula's most potent chemical crucible. Nestled within the already turbulent Kleinman Low region is an even more extreme environment known simply as the Orion hot core. It is not a core in the sense of a star's center, but a compact, blisteringly hot knot of gas and dust, only about 1/10,000th of a light year across. To put that in perspective, if the entire Orion Nebula were the size of a football stadium, the hot core would be a single grain of sand glowing on the field. Yet within that minuscule volume, temperatures soar to over 200 degrees Kelvin, which is remarkably hot for deep space. This intense heat comes from a deeply embedded, massive protostar, a stellar infant still hidden from view by an almost opaque shroud of dust. The star's fierce radiation has fundamentally transformed its immediate surroundings, turning it from a deep freezer into a roiling pressure cooker. For millions of years before this star ignited, the dust grains in this part of the cloud were like tiny icy satellites. They were coated in thick layers of frozen water, carbon monoxide, methane, and ammonia, accumulating molecule by molecule in the profound cold. But the birth of the massive protostar changed everything. Its rising heat acted like a cosmic blowtorch sweeping through the surrounding material. This sudden warming did not just melt the ices on those dust grains. It flash vaporized them, blasting the frozen molecules directly into the surrounding gas in an explosive instant. The result is a dense, seething soup where simple, frozen ingredients have been liberated and now float freely, colliding and combining in the hot, dense gas. This transition from solid ice to free-floating gas is absolutely critical. On the surface of a cold dust grain, two molecules might meet and stick, forming a simple bond. But in the chaotic, energetic environment of the hot gas phase, far more complex reactions become possible. The Orion hot core has become one of the richest interstellar chemical laboratories we know. Radio telescopes tuned to specific frequencies have identified a bewildering zoo of molecules here, many of them probiotic, meaning they are the precursors to the building blocks of life. We detect not just water and ammonia, but formaldehyde, methanol, and even molecules like methyl cyanide and vinyl alcohol. Some of these are surprisingly large and intricate for space, containing 8 or more atoms linked together. This tiny, scorching knot of gas is demonstrating that the harsh conditions around a newborn star are not just destructive. They are creatively chaotic, taking the simple frozen residues of the interstellar cloud and using raw stellar heat to forge them into a far more complex chemical broth. The material here will eventually be incorporated into new planetary systems, possibly seeding future worlds with a rich inheritance of organic compounds. It is a vivid reminder that the recipe for life may begin not in gentle ponds, but in the intense infernos of stellar birth. Amidst the nebula's familiar hues of red and blue, an unexpected color once appeared on the map. Data from the Spitzer Space Telescope revealed a strange, sprawling structure that astronomers dubbed the Orion Extended Green Object. This was not a subtle feature. It appeared as a vast, ghostly greenish glow, a diffuse emission that seemed to paint the nebula's background with an alien brushstroke. The color itself was a product of Spitzer's infrared filters. A specific wavelength of light assigned a green hue for our eyes to interpret, but the light's origin was genuinely puzzling. What process in this well-studied nursery could produce such a widespread monochromatic signal? For a time, it stood as a genuine enigma, a new piece on the board that did not seem to fit the established rules. The answer, when it came, connected this ethereal glow directly to the nebula's most violent nursery activities. The green emission was traced to a specific fingerprint in the infrared spectrum, a signature of molecular hydrogen gas that had undergone a tremendous shock. Molecular hydrogen is the primary ingredient of the cold Orion cloud, but it is normally very quiet and difficult to see, For it to glow, it must be violently stirred. The extended green object, therefore, is not a single thing, but a colossal map of turbulence. It traces the invisible battle lines where the supersonic jets from hidden protostars like those that create Herbig-Haro objects slam headlong into the stagnant walls of the surrounding molecular cloud. Each collision site heats the hydrogen molecules to thousands of degrees, causing them to vibrate and emit this specific infrared light. So this mysterious green glow is essentially the thermal aftermath of countless cosmic impacts, the bruised and glowing skin of the cloud where the fury of stellar birth leaves its mark. It shows us that the violence we see in isolated jets and bullets is not confined to small regions. It is a pervasive, almost ambient condition throughout the star-forming complex, a faint green testament to the relentless shockwaves constantly reshaping the cradle of new suns. The faint green glow of shocked hydrogen reveals a violent undercurrent, but to truly see the nebula's structure, we must look at what blocks the light. Cutting across the brilliant heart of the Orion Nebula are intricate, branching patterns of absolute blackness, features known as dark lanes. At first glance, they look like simple shadows, voids where the glowing gas has been scrubbed away. The reality is far more substantial and strange. These are not two-dimensional silhouettes painted on a flat canvas. They are immense, three-dimensional mountains and valleys of cold dust and gas, vast columns of material so dense they absorb all the visible light from the stars behind them. Their shapes are not random. The most prominent dark lanes, like the one forming the famous Orion Bar, have sharp, sculpted edges facing the trapezium stars, eroded by that intense radiation. But deeper within the nebula, the lanes twist into complex filamentary patterns, like rivers of ink flowing through a sea of light. These intricate shapes are a cosmic fingerprint, and they hold a direct clue to an invisible force. The dust grains within these lanes are not floating freely. They are aligned ever so slightly by the magnetic fields that thread the entire molecular cloud. Think of it like iron filings scattered near a magnet. The filings line up along the field lines, revealing the magnet's shape. In the nebula, elongated dust grains behave similarly, aligning themselves with the local magnetic field. As these aligned grains pile up, they preferentially block light along certain directions, causing the dark lanes to form in specific flowing patterns. Therefore, the sweeping curves and sharp ridges of the dark dust are not just accidents of density. They are a shadow map of the cloud's hidden magnetic skeleton. The lanes trace where the field is strongest, where it has guided the collapse of material and now channels the flow of stellar winds. This means the beautiful, textured tapestry of light and shadow we admire is in essence a colossal projection of magnetic forces, a visible trace of the invisible lines that shape the birth of every star within. Magnetic fields may shape the nursery, but gravity writes its most explosive stories. The violence within the Orion Nebula does not just forge bullets and shock waves, it can also fling entire stars into the void. Racing across our galaxy are several stellar fugitives, and their trajectories all point back to a single, dramatic event in Orion's heart. Stars like Ae Aurigae and Mu Columbae are not moving with the gentle drift of the Milky Way's rotation. They are screaming through space at speeds over 100 kilometers per second, blazing a path that, if traced backward in time, leads directly to the Trapezium Cluster. These are runaway stars, and they carry the unmistakable signature of a gravitational catastrophe. The most compelling theory to explain their furious flight is known as the binary collision. Imagine the Trapezium Cluster not as a peaceful family portrait, but as a crowded, chaotic dance hall in its youth. Within it, two separate pairs of stars, two tight binary systems, orbited each other in a complex gravitational embrace. In such a dense environment, close encounters are inevitable. According to the model, these two binary systems passed too near one another. What followed was not a simple bump, but a devastating gravitational tango. The immense shifting pulls from four massive stars interacting at close range can slingshot one or more of them outward like stones from a celestial catapult. In this scenario, the energy for their incredible speed comes not from an explosion, but from the orbital energy of the binaries themselves, a gravitational theft of monumental proportions. Computer simulations show that such an encounter could perfectly explain the observed paths and speeds of AE Aurigae, Mu Columbi, and even a third runaway 53 Arietes. They were not gently pushed out by stellar winds, they were violently ejected, likely within the same brief, chaotic moment over 2 million years ago. Today, they are solitary travelers separated by hundreds of light years from each other and from their birthplace, destined never to return. Their existence is a fossil record written in motion, proving that the nursery's beautiful glow is the aftermath of a stellar demolition derby whose participants are still flying apart. The gravitational chaos that ejected runaway stars is just the most visible symptom of a far more widespread condition. The Orion Nebula is not merely a backdrop for its famous trapezium stars. It is the core of a vast, seething stellar metropolis known as the Orion Nebula Cluster. Here, thousands of young stars, from brilliant giants to faint red dwarfs, are packed into a region only a few light years across. To grasp the density, imagine taking every star within several hundred light years of our Sun and cramming them all into the space between our solar system and its nearest stellar neighbor. The result would be a night sky blazing with hundreds of stars as bright as Venus, with many so close they would be visible in daylight. This is the reality for any hypothetical planet born within this cluster. In such a crowded environment, stars are not solitary actors. They are participants in a relentless gravitational dance. Close encounters are not rare accidents. They are a fundamental part of life in this stellar city. When two stars pass near each other, their mutual gravity acts like a slingshot, altering their paths forever. A gentle, circular orbit can become a wild, elongated ellipse. A slow-moving star can be hurled toward the cluster's center, while another might be flung out toward the sparse suburbs, its velocity forever changed by a brief gravitational handshake. This constant gravitational shuffling has profound consequences for the cluster's architecture and longevity. The most massive stars, like those in the trapezium, tend to sink toward the center through a process called dynamical friction, their great weight dragging them into the densest core. Meanwhile, lighter stars are more easily scattered, contributing to a gradual evaporation of the cluster's outer regions over millions of years. But the true casualty of this chaos may not be the stars themselves, but the families they are trying to build. For every star with a protoplanetary disk, a close stellar flyby is a potential disaster. The gravitational tug from a passing star can stretch, warp, or even tear apart a delicate disk of gas and dust. It can fling nascent planets into wildly eccentric orbits, send them crashing into their star, or eject them entirely into the interstellar void as rogue planets. A planetary system that forms in the serene outskirts of the cluster might be stable for 1 million years, only to have its entire architecture rewritten by a single, uninvited stellar guest passing too close. This raises a haunting question for our own existence. Our solar system formed in a much more tranquil, sparse environment. Had our Sun been born in a dense cluster like Orion, the gravitational tides from stellar neighbors could have easily disrupted the orderly formation of Jupiter, Earth, and the other planets. The very conditions that forge stars in spectacular numbers may also be hostile to the stable, long-term development of life-bearing worlds. The Orion Nebula Cluster is a breathtaking spectacle of collective birth, but it is also a cosmic lesson in celestial real estate, demonstrating that where you are born dictates the destiny of everything you might create. That sharp boundary of the Orion Bar is not merely a scenic ridge. It is a war zone on the atomic scale, a place where light itself acts as a cosmic butcher. This is the photodissociation region, and the physics at play here are as intense as they are beautiful. The front line is defined by the torrent of ultraviolet photons screaming from the trapezium stars. When these high-energy bullets of light slam into a stable molecule like molecular hydrogen drifting in from the dark cloud, the impact is catastrophic. The photon does not gently nudge the molecule apart. It delivers a precise, violent blow, severing the chemical bond that holds the two hydrogen atoms together. In an instant, a stable molecule is shattered into two separate, energetic atoms. This is photodissociation, the relentless disassembly of matter by starlight. The process does not stop with hydrogen. Any molecule venturing too close to this brilliant edge of water, carbon monoxide, complex organics, meets the same fate. The ultraviolet radiation acts like a cosmic eraser, scrubbing the area clean of molecular complexity and leaving behind a soup of ionized atoms and free radicals. But step just behind this eroding front into the shadow of the bar itself, and the environment transforms. Here, the starlight is filtered, its most destructive photons already spent. The gas is cooler, denser, and shielded. In this narrow refuge, a frantic new chemistry begins. The atoms and molecular fragments blasted apart at the front now collide in the dark. Without the constant ultraviolet assault to break them apart again, they can stick together, forming new and often more complex molecules than existed before. This transition zone becomes a prolific cosmic factory. Simple carbon atoms link with hydrogen to form methylidyne radicals. Oxygen snatches up hydrogen to reform water ice on dust grains. Astronomers have even detected the spectral fingerprints of small organic molecules here, forged in this narrow strip between annihilation and creation. The Orion Bar, therefore, is a dynamic engine of chemical recycling. It is not a static wall. It is a propagating front, a wave of destruction that simultaneously seeds the conditions for new molecular birth just behind it, proving that in the nebula, the most fertile ground often lies directly in the shadow of the apocalypse. This same photodissociation front at the bar is now revealing a hidden bombardment from across the galaxy. The complex molecules forming in its shadow are doing more than just surviving, they are acting as natural Geiger counters. Recent research suggests the bar's specific molecular emissions can be used to measure the relentless flux of cosmic rays penetrating the nebula's heart. Cosmic rays are not rays of light, they are atomic nuclei, mostly protons, accelerated to nearly the speed of light by distant supernova or black holes. They are the most energetic particles in the universe, and they rain down on everything, including the Orion Nebula. But they are notoriously difficult to study directly because their paths are scrambled by the galaxy's magnetic fields, hiding their origins. We cannot simply point a telescope and see them. We need to see what they do, and that is where the Orion Bar's unique chemistry becomes a detective tool. When a high-energy cosmic ray smashes into a dense cloud like the bar, it does not just bounce off. It tears through the gas, colliding with molecules and leaving a trail of ionization in its wake. This ionization is like a spark in a chemical mixture. It energizes the gas and triggers specific chemical reactions that would otherwise happen very slowly or not at all. In particular, it can boost the formation of certain molecular ions like H3+, which is a hydrogen molecule with an extra proton. The amount of these ions present is directly linked to the intensity of the cosmic ray bombardment. By carefully measuring the faint radio and infrared emissions from these special molecules in the bar, astronomers can essentially take a reading of the local cosmic ray dose. It is like measuring the brightness of a glow stick to determine how much chemical activator was inside. This provides an indirect but incredibly valuable way to study these ghostly high-energy particles from across the galaxy. The bar becomes a fixed laboratory in space, allowing us to answer a critical question. Is the cosmic ray flux in a violent star-forming region like Orion higher than in the quiet interstellar space near our solar system? the answer could reshape our understanding of how cosmic rays influence the chemistry of entire galaxies and even affect the conditions for planet formation in the most active stellar nurseries. Between us and the brilliant tapestry of the Orion Nebula hangs a ghost. It is a faint, diaphanous curtain of gas known to astronomers as the Orion Veil. This is not part of the main nebula itself, but a separate foreground screen of mostly neutral hydrogen and helium, drifting in the vast space that separates our solar system from the stellar nursery over 1,300 light-years away. For centuries, its presence went unnoticed. Its subtle glow blended seamlessly into the nebula's own radiance. But with modern instruments and careful analysis, we have come to understand it as a distinct entity, a separate chapter in the story written along our line of sight. The veil is being illuminated not from within but from behind. The fierce ultraviolet radiation from the trapezium stars, having traveled across the cavity of the main nebula, continues its journey outward until it strikes this distant, tenuous sheet. The light acts like a cosmic projector, causing the veil's atoms to fluoresce with a soft, pervasive glow. In some areas, the radiation is so intense it is actually stripping electrons from the atoms, ionizing parts of the veil and creating a secondary, fainter version of the processes happening in the nebula proper. This creates a fascinating complication for astronomers. When we look at the Orion Nebula, we are not seeing a single, unified object at a single distance. We are seeing a complex superposition, a celestial double exposure. The bright loops and dark lanes of the main nebula are viewed through this shimmering foreground veil. Its subtle structures can enhance certain features, add faint halos of light, or subtly alter the colors and contrasts we perceive. Disentangling the light from the veil from the light of the nebula behind it is a meticulous task, like trying to study a brilliant stained glass window while a thin, glowing scrim hangs a few feet in front of it. Yet this complication is also a gift, because the veil is a simpler, quieter environment than the turbulent nebula. It serves as a clean laboratory. By studying how the trapezium's light filters through and interacts with this isolated gas cloud, scientists can better understand the precise properties of that starlight itself and measure the detailed physics of ionization in a more controlled setting. The Orion Veil reminds us that space is never truly empty, and that every majestic vista is layered with history, each layer telling its own quiet story. That foreground veil is not the only screen altering our view of the nebula's drama. On the opposite side of the glowing cloud, another sharp feature carves its own bright line against the darkness. Astronomers call it the Orion Bar, a name that sounds like a simple description but marks a distinct and fascinating structure. While the famous Orion Bar slices vertically through the nebula's heart near the trapezium, the bright bar forms a brilliant horizontal rim along the nebula's western edge. It is essentially a cosmic shoreline, a place where the sea of light from the central stars meets a separate, dense wall of cold molecular gas. This is another ionization front, a sibling to the main bar, but playing out its story on a different stage. The physics are the same titanic struggle. Intense ultraviolet radiation from the trapezium stars, having traveled farther across the nebula, finally slams into this distant cloud bank. The starlight excites and ionizes the atoms at the very surface, causing that thin skin to fluoresce with a fierce, crisp glow. This creates the bright rim we see, a razor-thin line separating the luminous nebula from the opaque darkness behind it. But look closely and you will see the bright bar is not perfectly smooth. It has texture, subtle curves, and faint tendrils of glowing gas streaming away from it. These are the signs of erosion in action. The radiation is not just lighting this cloud, it is evaporating it. The fierce photons are blasting molecules apart and driving a wind of hot gas off the cloud's surface, slowly sculpting and dissolving the dense material over millennia. This ongoing destruction makes the bright bar a dynamic laboratory. Because it is seen almost edge-on from our perspective, It gives astronomers a clean, side-on view of the structure of an ionization front. They can study how the transition from hot, ionized gas to cold, neutral molecules happens across a very narrow space, sometimes in less than the distance between our Sun and Pluto. In the intricate geography of the Orion Nebula, the bright bar stands as a reminder that the battle between light and shadow is not a single event, but a siege being waged on multiple fronts, each wave of starlight etching its own bright scar into the cosmic landscape. The brilliant glow we see is only a fraction of the nebula's true energy. To witness its most violent temperament, we must look with entirely different eyes. The Chandra X-ray Observatory has done just that, peeling back the nebula's serene visual facade to expose a seething, high-energy underworld. In X-ray light, the Orion Nebula transforms into a battlefield. The familiar loops of gas are gone, replaced by a speckled, crackling landscape of point-like sources swimming in a faint, diffuse haze. Each of those brilliant points is a young star, but not as we know them in visible light. Their X-ray emission comes not from their surfaces, but from their coronae, the superheated, magnetically dominated outer atmospheres. For stars like our Sun, the corona is a thin, million-degree layer. For the tempestuous toddlers of the Trapezium Cluster, it is a raging inferno. Their magnetic fields are tangled and dynamic, constantly snapping and reconnecting in colossal loops that stretch far into space. Each reconnection is a cataclysm, a magnetic short circuit that releases energy equivalent to millions of hydrogen bombs, heating pockets of plasma to tens of millions of degrees and producing a fierce flare of X-rays. These stars do not flare occasionally like our Sun. They flare constantly in a relentless, stormy barrage. The diffuse haze that fills the Chandra image between the stars tells an even more dramatic story. This is not empty space glowing. This is the interstellar gas itself, heated to millions of degrees. The source is the unimaginably powerful stellar winds from the massive trapezium stars. When these supersonic rivers of charged particles, screaming outward at over 1,000 kilometers per second, collide with each other or slam into slower-moving nebula gas, the impact is so violent it generates shockwaves that heat the material to X-ray emitting temperatures. It is a continuous galaxy-scale collision, a perpetual thermal roar underlying the visible beauty. This X-ray vision fundamentally changes our understanding of the nursery's environment. Any young planet forming here is not just bathed in gentle starlight. It is being continuously irradiated by a hail of high-energy X-rays and immersed in a fog of seething million-degree plasma. This harsh bath could strip away nascent atmospheres or stimulate complex chemistry in unexpected ways, painting the conditions for planet formation in the most extreme colors imaginable. X-rays reveal a violent stellar temperament, but to see the nebula's true substance we must listen to its coldest, quietest song. Switch from the searing vision of Chandra to the patient ear of a radio telescope, and the Orion Nebula transforms once more. The brilliant glow vanishes, replaced by a detailed map of shadow and mass. Radio waves pierce the opaque veils of dust that block visible light, allowing us to see deep into the heart of the molecular cloud itself. What emerges is not a picture of light but of structure and motion. We see the vast filamentary bones of OMC1, the cold dark lanes not as silhouettes but as three-dimensional rivers of gas, dense and frigid. This is the nursery's raw material, the hydrogen molecules and dust that have yet to be touched by starlight, mapped in exquisite detail by their faint radio whispers. Specific molecules like carbon monoxide become our guides, each emitting a unique radio signature that tells us not only where the gas is, but how it is moving. By measuring the subtle shifts in the frequency of these radio emissions, a phenomenon called the Doppler effect, astronomers can create a velocity map of the entire cloud. We can see which filaments are collapsing inward, feeding the growing protostars, We can trace the supersonic expansion of gas blasted out by stellar winds and jets, watching as bubbles of hot gas push against the cold molecular walls. This radio view reveals the nebula's immense hidden mass, far greater than what is visible in the glowing ionized gas. It shows the complex, churning dynamics beneath the beautiful facade, the slow, gravitational inflows and the violent, directional outflows that are constantly reshaping the stellar cradle. In radio light, the Orion Nebula is no longer just a luminous painting. It is a detailed architectural blueprint showing the weight, the framework, and the silent, powerful currents that are building its future. Radio maps reveal the cloud's hidden mass, but to see its living, breathing heart, we must look in the warmth it gives off. The visible nebula is merely the glowing skin. Its true anatomy lies buried, visible only in the infrared. This is where telescopes like Spitzer and now the James Webb Space Telescope become our most profound eyes. They see not by reflected starlight, but by the heat emitted by the dust itself and the faint glow of objects too cool to shine in visible light. The result is a revelation that rewrites the entire story. The familiar landscape of glowing gas dissolves, replaced by a cavernous, intricate architecture. Thick pillars and vast walls of dust, dark and imposing in visible light, now glow with an ethereal, rusty orange light, backlit by the embedded warmth of millions of stars. This is the nebula's skeleton, the dense filamentary network that radio maps hinted at, now rendered in stunning, three-dimensional relief. These are not passive structures. They are the gravitational highways along which material flows, collapsing into knots that will become the next generation of stars. The infrared view strips away the surface glare to expose the nursery's bustling population. Suddenly, the space between the bright trapezium stars fills with countless faint, pinpoint sources. Many are deeply embedded protostars, so young they are still swaddled in thick cocoons, their light entirely converted to heat by the surrounding dust. Others are far more mysterious, objects too faint and cool to be true stars. These are the brown dwarfs, the failed stars of the cosmos. They are balls of gas that condensed like stars but never gathered enough mass to ignite sustained nuclear fusion in their cores. They glow only with the residual heat of their formation, a dim, fading ember in the infrared. In the crowded halls of the Orion Nebula cluster, the James Webb Telescope is finding them in startling numbers, suggesting these substellar objects may be a common, if hidden, outcome of the star formation process. They exist in a shadowy realm between giant planet and true star, a population once theorized but now vividly mapped, proving that for every brilliant sun that lights the nebula, there may be several of these dark, wandering giants fading quietly in the dust. Even the nebula's X-ray fury is filtered through a cooler, pervasive haze. To trace the source of that glow, we must step up in energy to the ultraviolet spectrum. Here, the view from instruments like the Hubble Space Telescope's cosmic origin spectrograph is not one of gentle fluorescence, but of searing, atomic-level violence. The familiar reds and blues of the nebula give way to a landscape sculpted by pure, raw heat. Ultraviolet light reveals the hottest gas, material heated to tens of thousands of degrees by the direct, unshielded blast of the trapezium star's most energetic photons. In this harsh light, the delicate loops and filaments of the visible nebula sharpen into stark, intricate relief. The ionization fronts, like the Orion Bar, become razor-sharp boundaries in ultraviolet, their complex, layered structure laid bare. We can see exactly where the flood of ultraviolet radiation is being absorbed, atom by atom, mapping the advancing edge of this cosmic fire as it eats into the cold molecular cloud. But the ultraviolet view offers more than just a sharper picture. It provides a detailed chemical autopsy. When the spectrograph splits the ultraviolet light into its constituent colors, it reveals dark lines and bright spikes, the unique spectral fingerprints of specific elements. These are not just hydrogen and helium. The data shows clear signatures of carbon, nitrogen, oxygen, silicon, and iron, all floating in the hot gas. This is the recycled debris of stellar life and death. These heavier elements were forged in the nuclear furnaces of previous generations of massive stars, then blasted into space by supernova or powerful winds long before the Trapezium Cluster was born. Now, that enriched material is part of the nebula's raw stock. The intense ultraviolet radiation from the new massive stars is stripping electrons from these atoms, exciting them, and causing them to emit their own telltale ultraviolet glow. We are witnessing the heavy elements from dead stars being violently stirred back into the cosmic pot, ready to be incorporated into a new generation of stars, planets, and perhaps one day living things. The ultraviolet eye shows us that the nebula is not just a birthplace, it is a grand recycling center where the ashes of ancient giants become the foundation for all that follows. The ultraviolet fingerprints of recycled elements provide more than just a history lesson. They establish a universal standard. For astronomers deciphering the chemical makeup of the cosmos, the Orion Nebula has become an indispensable benchmark, a cosmic Rosetta Stone. Its proximity and brightness offer a rare opportunity to measure the fundamental ingredients of star-forming gas with exceptional precision. Think of it as a master sample in a laboratory. Before you can analyze an unknown substance from a distant land, you first need a pure, well-understood reference sample to calibrate your instruments. Orion serves as that pristine reference for the entire universe. By meticulously dissecting its light with spectrographs, scientists can determine the exact abundances of key elements like helium, oxygen, carbon, and nitrogen within its glowing gas. They can ask and answer questions with startling accuracy. For every 1 million hydrogen atoms in the Orion Nebula, how many oxygen atoms are present? The answer creates a baseline number, a chemical signature for a typical, nearby region of active star formation in our own Milky Way galaxy. This is profoundly important because we cannot travel to other galaxies to take direct samples. When we point our telescopes at a brilliant star-forming region in a distant spiral galaxy 10 million light-years away, the light we collect is faint and blended. Its spectral lines are messy, its signals weak. To interpret that data, astronomers compare it directly to their high-fidelity template, the Orion Nebula. If the ratios of helium to hydrogen or oxygen to neon match the Orion benchmark, it suggests that galaxy's interstellar soup is chemically similar to our own local neighborhood. Significant deviations, however, tell a story of a different cosmic history. Perhaps that distant galaxy is older, with more generations of stars having lived and died, enriching its gas with more heavy elements. Or perhaps it is younger, still cooking its first batches of metals. By using Orion as a fixed point of comparison, we can begin to map the chemical evolution of the universe itself, tracing how the elemental building blocks of planets and life have changed from galaxy to galaxy and across cosmic time. This one glowing cloud in our backyard has become the standard against which we measure the elemental richness of the entire visible cosmos. That cosmic Rosetta Stone is fixed at a precise location, but pinning down exactly how far away it sits has been one of astronomy's longest-running detective stories. The distance to the Orion Nebula is not just a number for a catalogue, it is the master key that unlocks the true nature of everything within it. For centuries, astronomers had only the crudest tools to measure such vast spans. Early estimates were little more than educated guesses based on the nebula's apparent size and assumed intrinsic brightness. Some placed it just a few hundred light-years away, while others thought it might be a distant island universe far beyond our Milky Way. The breakthrough began with the work of astronomers like Edwin Hubble in the early 20th century. By identifying variable stars within the nebula and comparing their apparent brightness to similar stars with known distances, he provided a more solid, though still imprecise, yardstick. This placed Orion firmly within our galaxy, but the exact figure remained fuzzy, with estimates ranging from 1,000 to over 2,000 light-years. The uncertainty had profound consequences. If you do not know how far away a light bulb is, you cannot tell if it is a dim bulb nearby or a brilliant beacon far away. An incorrect distance meant astronomers were misjudging the true luminosity, size, and mass of the trapezium stars and the entire nebula complex. They could not accurately calibrate the fundamental relationships between a star's mass, its temperature, and its energy output, the very equations that describe how stars live and die. The quest for a precise distance became a critical mission. The modern solution arrived with the power of parallax, one of the most fundamental and reliable techniques in the astronomer's toolkit. The concept is elegantly simple. Hold your finger in front of your face and close one eye, then switch eyes. Your finger appears to jump against the background. The amount of that shift depends on how far away your finger is. For stars, astronomers use Earth's orbit around the Sun as their two viewing points. They observe a target star, like one in the Orion Nebula cluster, from opposite sides of Earth's orbit, 6 months apart. Against the backdrop of much more distant stars, the target star appears to wiggle slightly. The tinier that wiggle, the farther away the star is. For an object as distant as Orion, that wiggle is incredibly small, a fraction of a millisecond, like measuring the width of a human hair from over 10 miles away. This requires extraordinary precision, delivered by space-based observatories like Hipparcos and, more recently, the Gaia mission. Gaia has meticulously mapped the positions and motions of over 1 billion stars, and its data for the stars in the Orion complex has been transformative. By averaging the parallax measurements for many member stars, astronomers have converged on a remarkably precise value. The heart of the Orion Nebula, the Trapezium Cluster, is now known to be 1,344 light-years from Earth, with an uncertainty of only about 20 light-years. This hard number is the foundation upon which all other knowledge is built. It allows scientists to calculate the true, breathtaking luminosity of the trapezium stars, confirming they are indeed monstrously powerful young stellar objects. It lets them accurately gauge the physical size of the nebula's cavities and pillars and determine the masses of its protostars from their observed motions. Every model of star formation, every theory about how stellar winds shape nebulae, and every estimate of how many stars are being born within that cloud relies on this one crucial measurement of distance. What began as a point of light in a fuzzy patch of sky is now a precisely located laboratory, its scale finally understood, allowing us to read its story with perfect clarity. That precise distance of 1,344 light-years places the Orion Nebula within a uniquely intimate cosmic context. It is not just another entry in a catalogue. It is the closest massive star-forming region to our solar system, a grand stellar nursery sitting right in our galactic neighborhood. This proximity transforms it from a distant spectacle into a foundational classroom. For countless generations before telescopes, it was already there in the winter sky, a persistent smudge at the center of Orion's sword. That fuzzy patch, visible to the naked eye even from moderately light-polluted areas, was a mystery waiting to be solved. Early star charts and cultural myths often noted its non-stellar quality, a hint that the heavens held more than just points of light. When Galileo first turned his spyglass toward it in 1610, he could only resolve a cluster of tiny stars within the glow, not understanding the luminous mist that surrounded them. It took the larger telescopes of later centuries to begin revealing its true nature as a vast cloud of glowing gas. This accessibility made it the perfect laboratory. Because it is so close and so bright, we can study its processes with a resolution impossible for any other similar nebula. Every detail in the Trapezium Cluster, every ripple in the ionization front, every faint protostar at the edge of detection is seen with stunning clarity. This has allowed astronomers to construct the modern playbook for star formation. The violent stellar winds carving cavities, the evaporation of protoplanetary disks, the triggered collapse of new stars at the edges of bubbles, the rich chemistry in photodissociation regions, these were not abstract theories. They were principles first observed and confirmed in vivid detail within the Orion Nebula. It taught us that stars are not eternal fixtures, but are born in dense, dusty clouds, and that our own sun began its life in a similar, if less grandiose, stellar nursery over 4.5 billion years ago. When we look at Orion, we are not just looking at a beautiful object. We are looking into a mirror that reflects the violent, creative origins of every star, including our own and every planet that orbits them. It is the cosmic landmark that first answered humanity's oldest question about the night sky. What are those lights? By showing us where they come from. Long before telescopes defined its nature, that glowing smudge in Orion's sword spoke a universal language. Cultures across the world wove its persistent, non-stellar light into their stories of gods and heroes. In ancient Mesopotamia, it was linked to the god Marduk, a symbol of cosmic authority. For many indigenous cultures in the Americas, it was often seen as smoke or embers from a great celestial fire, a campfire of the gods, or the glowing debris from a mythical hunt. The Maori of New Zealand saw it as the stern of the great canoe of Tamariti, scattered with glowing pebbles to become the stars. These interpretations shared a common thread, a recognition that this was not a pure, sharp point of light, but something diffuse, something with substance. It was an anomaly in the perfect clockwork of the stars, and the human mind instinctively filled that ambiguity with narrative, transforming a cloud of gas into smoke, fire, or celestial artifacts. This cultural tapestry set the stage for a profound shift in understanding, one that would move the nebula from the realm of myth into the forefront of scientific revolution. When astronomers like Christian Huygens and Giovanni Hodierna began sketching it in the 17th century, they were documenting a new kind of celestial object. But the true turning point arrived with the invention of photography. In September 1880, the American astronomer Henry Draper performed a monumental feat. Using a dry plate photographic process and an 11-inch refracting telescope, he captured a 51-minute exposure of the Orion Nebula. That image, grainy and historic, was the first ever deep space photograph of a nebula. It was not just a picture, it was a permanent record, freezing the nebula's intricate structure in a way no human eye at an eyepiece ever could. For the first time, astronomers could compare its details side by side, measure its features, and study its light at their leisure. Draper's photograph, and the better ones that swiftly followed, transformed the Orion Nebula from a visual spectacle into a data set. It became a laboratory subject, its filaments and shadows available for meticulous analysis. This directly enabled the groundbreaking work of astronomers like William Huggins, who, just a few years later, pointed his spectroscope at the nebula and discovered its light was not a continuous spectrum like a star's, but the bright line emission of glowing gas. That single observation proved it was not a distant cluster of stars too faint to resolve, as some had thought, but a vast, luminous cloud of matter in its own right. The fuzzy spot in the sword was now understood as a physical place, a cosmic entity, and its photograph was the catalyst that changed everything. That photograph revealed a place, but its deeper truth is that it reveals a time. The Orion Nebula is more than a distant spectacle. It is a time capsule, a window into the very conditions that forged our own existence. When we peer into its chaotic heart, we are not just watching other stars being born. We are looking back at the violent, radiant nursery where our sun and its family of planets first took shape over 4.5 billion years ago. The infant sun was almost certainly not born in isolation. It was likely a member of a modest stellar cluster, much like the Orion Nebula cluster, though perhaps less dense and grand. This means the environment of our solar system's infancy was nothing like the serene, empty space we occupy today. It was a crowded, dangerous, and brilliantly lit neighborhood. The furious ultraviolet radiation from massive sibling stars would have bathed our protoplanetary disk, just as the trapezium's light bathes the proplyds we see today. The powerful stellar winds from those giants would have howled through the solar system's outskirts, sculpting and eroding the disk of gas and dust from which the planets were coalescing. We can see this process in action right now in Orion, watching as proplyds are photoevaporated, their precious planetary material streaming away in long, comet-like tails. For our own solar system to have survived, our Sun must have drifted away from its most massive and destructive siblings relatively quickly, escaping the harshest glare before our planet-forming disk could be completely stripped away. The planets we have today, from rocky Mercury to gaseous Jupiter, are the survivors of that cosmic gauntlet. By measuring the evaporation rates of proplyds in Orion, astronomers can calculate the clock. They can determine how long a disk like ours might have had to form giant planets before the environment destroyed its gaseous component. This suggests the race to build a Jupiter may have been frantic, completed within just a few million years, a mere blink in cosmic time. The nebula's radiation also provides a clue to a great mystery in our own asteroid belt. Many meteorites found on Earth show evidence of being heated and altered by a powerful, short-lived source of radiation in the solar system's first million years. For decades, the source was unknown. Could it have been an early, hyperactive sun? Observations of Orion's young stars suggest a more dramatic answer. The most massive stars in a cluster often undergo colossal flares during their earliest years, outbursts that flood the entire region with intense X-rays and gamma rays. If our Sun had such a massive stellar neighbor, its violent tantrums could have been the cosmic oven that baked the asteroids, imprinting a radioactive signature we still find in ancient space rocks today. So every detail we catalog in Orion, the speed of the winds, the intensity of the radiation, the crowded stellar dynamics, is not just data about a faraway place. It is a forensic tool. We are using this brilliant nearby nursery as a reference to run the tape of our own origins backward, to reconstruct the tumultuous, irradiated, and wind-swept cradle that ultimately gave us a stable star, a blue planet, and ourselves. The brilliant chaos of the Orion Nebula is not a permanent fixture. Its beauty is a fleeting firework in the slow time of the galaxy, and its fate is written in the very stars that give it light. The same intense radiation and supersonic winds that sculpt its pillars and evaporate protoplanetary disks are also sealing its doom. Over the next few million years, this relentless onslaught will perform a cosmic clean-up operation of staggering scale. The massive trapezium stars will continue to blast the surrounding cloud with ultraviolet photons, stripping electrons from atoms and heating the gas to escape velocity. Their hurricane-force stellar winds will act like a celestial plow, pushing the vast reservoirs of hydrogen and dust outward, dispersing them back into the interstellar medium from which they came. The process will be gradual but inexorable. First, the most tenuous outer filaments will fade and vanish, their glow extinguished as the gas is either ionized into invisibility or blown away. Then, the iconic pillars and the dark lanes will be eroded from the outside in, their intricate shapes dissolving as the supportive gas around them is stripped away. Finally, even the dense core of the molecular cloud, OMC1, will be exposed and dismantled. The nebula's luminous glow, which comes from that very gas being excited, will dim and flicker out as its fuel is exhausted. What we now see as a vast, glowing cloud will one day simply vanish, leaving behind only the stars it created. In its place will be a sparkling open cluster, a loose grouping of stars drifting through space, looking much like the famous Pleiades cluster we see today. The trapezium stars, having consumed their nuclear fuel at a prodigious rate, will be long gone, ending their short lives in spectacular supernova. But hundreds of their smaller, longer-lived siblings, The Sun-like stars and red dwarfs will remain orbiting each other in a gentle gravitational dance, a permanent monument to the nursery that once was. Yet the story does not end there. The gravitational slingshots that created runaway stars like Aorighi are not events of the distant past. They are an ongoing process in the crowded cluster. As the stars continue their dynamic dance, more close encounters will inevitably fling additional stars out into the galactic void. These stellar fugitives, catapulted from their birthplace, will carry with them a unique signature. Their chemical composition, the specific ratios of elements like oxygen, carbon, and iron in their atmospheres, will be an exact match for the enriched soup of the Orion Nebula. For the rest of their multi-billion-year lives, as they sail alone through the spiral arms of the Milky Way, they will bear this indelible fingerprint. An astronomer in the far future, measuring the light from one of these ancient wandering suns, could analyze its spectrum and declare with certainty, this star was born in the great Orion Nebula. The nursery's legacy, therefore, will not be confined to a single patch of sky. It will be scattered, one runaway star at a time, across the entire galaxy, a diaspora of orphaned suns, each telling the story of the brilliant, violent cradle that once lit up the winter sky. This cosmic cradle of suns may also be a crucible for life's ingredients. Within the nebula's turbulent clouds, a rich and complex organic chemistry is unfolding, forging the very molecules that could one day seed living worlds. Radio telescopes have catalogued a veritable zoo of carbon-based compounds swirling in the cold, dark cores and the hot, dense knots near newborn stars. We find simple molecules like hydrogen cyanide and formaldehyde, and more complex structures like methanol and even vinyl alcohol. These are not just random chemicals, they are the fundamental building blocks for amino acids and nucleobases, the organic Lego bricks from which proteins and genetic material are assembled. The processes we see in Orion, from ices vaporizing on warm dust grains to shock-driven reactions in turbulent gas, are likely universal recipes written into the fabric of every stellar nursery. This suggests that the raw materials for life are not rare cosmic accidents, but a standard byproduct of star and planet formation, scattered liberally across the galaxy. Yet there is a profound and sobering paradox at play. The very engine that drives this creative chemistry also renders the nebula's inner sanctum a death zone for life as we understand it. The intense ultraviolet radiation from the trapezium stars, which energizes the nebula's glorious glow, is a brutal sterilizing force. For any hypothetical planet forming close to these massive stars, or even within the evaporating proplyds we can see, this radiation would be apocalyptic. It would shred complex organic molecules as quickly as they form, strip away atmospheres, and bathe surfaces in a relentless, cell-destroying fury. Life as we know it, based on delicate carbon chemistry and liquid water, could not persist in such an irradiated environment. The search for life here, therefore, becomes a search for refuges. Astrobiologists look to the outskirts, to the colder, shielded depths of the molecular cloud where future solar systems may coalesce in quieter neighborhoods. They speculate about moons orbiting giant planets, whose icy shells might protect subsurface oceans from the stellar glare. The story of Orion teaches us that the universe may be generous with life's ingredients, but brutally selective about where it allows those ingredients to assemble into something alive. The nebula offers both a promise and a warning, the promise that the seeds of biology are sown in the fires of creation, and the warning that only in the sheltered shadows might those seeds ever take root. Its role as a symbol of cosmic wonder extends far beyond the pages of scientific journals. For generations, the Great Orion Nebula has served as a canvas for the human imagination, its glowing visage appearing in countless works of science fiction and art. In films, it often looms in the viewport of a starship as a breathtaking, swirling maelstrom of color, a visual shorthand for the sublime beauty and terrifying scale of deep space. In novels, it is depicted as a mysterious destination, a place where ancient alien ruins might be hidden within its luminous folds or where terrifying cosmic entities could be born. This artistic adoption is not accidental. The nebula's real, tangible beauty provides a perfect bridge between the known and the unknown. It is a real place we can point to in the night sky, yet its true nature, a violent stellar nursery, feels inherently dramatic and otherworldly. When a filmmaker uses the Orion Nebula as a backdrop, they are tapping into a deep, pre-existing sense of awe. They are using a real scientific marvel to ground their fictional universe, making the extraordinary feel plausible. This cultural resonance performs a vital, often overlooked function. For every young person who first encounters the nebula in a movie or a book, that image can spark a lifelong curiosity. That fictional starship flying toward its glow plants a seed, a question. What is that place really like? That question can lead to a telescope, to a textbook, to a career. The nebula, in this way, becomes more than an astrophysical object. It becomes a shared cultural icon, a gateway that transforms cold data into a story of adventure and discovery, inspiring the next generation of scientists, artists, and explorers to look up and wonder what else is waiting in the light. Against the brilliant backdrop of the nebula, some of the youngest stars reveal themselves not by their light but by their shadow. These are the silhouette disks, dark smudges that look like cosmic inkblots floating in the sea of glowing gas. Each one is a protoplanetary disk seen in perfect, edge-on alignment from our perspective. The central newborn star is hidden directly behind the thick, dusty pancake of material swirling around it. That disk, which could be wider than our entire solar system, is so dense it completely blocks the intense light from the nebula and the trapezium stars behind it. We see it as a crisp, black silhouette, a void against the light, often with a faint, ethereal glow of reflected starlight highlighting its top and bottom edges. This geometry is a gift to astronomers because it provides a clean, side-on view of a disk structure without the overwhelming glare of the central star. We can study their shapes, their thickness, and even trace how the material within them is distributed, all from the simple, profound fact that they are caught in a cosmic shadow play. These dark silhouettes are the quieter, more stable cousins of the evaporating proplyds we see face-on. They represent an earlier or more sheltered phase where the disk is still largely intact, a full pantry of planet-building material waiting to be used. From the hearts of these same deeply embedded stellar infants come eruptions of unimaginable precision. While massive stars blast out wide, chaotic winds, the youngest protostars produce something far more focused, microjets. These are not the diffuse outflows of older stars. They are narrow, needle-like beams of gas, often only a few times wider than our solar system, but stretching for trillions of miles. They are launched at velocities of hundreds of kilometers per second, not from the star's surface, but from the innermost regions of the swirling accretion disk. As material spirals down toward the newborn star, powerful magnetic fields channel some of it away along the star's poles, funneling it into these incredibly collimated jets. We cannot see them in ordinary visible light. To find them, astronomers must look at very specific wavelengths of light emitted by hot hydrogen or ionized sulfur, spectral lines that act like a highlighter pen for shocked, fast-moving gas. In these narrow views, the microjets suddenly appear as faint, thread-like structures, often in pairs shooting in opposite directions from the hidden protostar. They are the protostar's release valve, a way to shed excess spin and magnetic energy as it greedily gathers mass. Their existence is a critical clue. The fact that they are so narrow and fast tells us the launching mechanism is extraordinarily efficient and organized, a fundamental process that seems to be a universal part of how a star is born, from the smallest red dwarf to the largest blue giant waiting in the wings of the nebula's dark core. The violent tantrums of newborn stars are not confined to the hidden giants. Among the thousands of smaller, sun-like stars in the Orion Nebula cluster, a different kind of storm erupts with shocking regularity. These are the flare stars, and they are cosmic toddlers in the throes of magnetic growing pains. Unlike our stable, middle-aged sun, these young stars are spinning rapidly, their interiors churning like dynamos. This generates magnetic fields of immense complexity and strength, fields that become tangled, stressed, and stretched across the star's surface. When these magnetic lines of force snap and reconnect, they release catastrophic bursts of energy across the entire electromagnetic spectrum. What we observe as a flare is a detonation that can, in mere minutes, make the star hundreds of times brighter in X-rays and ultraviolet light. A single one of these eruptions can unleash more energy than 1,000,000 of the largest solar flares ever recorded from our own sun. For any fledgling planets orbiting such a tempestuous star, the environment would be apocalyptic. These flares would bathe young worlds in sterilizing radiation, strip away nascent atmospheres, and potentially trigger complex probiotic chemistry in a chaotic, unpredictable cycle of creation and destruction. The sheer frequency of these outbursts in Orion paints a picture of stellar infancy as a time of relentless magnetic fury, a phase every star, including our sun, must have passed through in its youth. This flickering starlight does more than just threaten hypothetical planets. It can paint the very nebula around it with shifting shadows and light. There exists a special class of reflection nebula whose appearance is not constant but changes over months or years. They are known as variable nebulae, and their behavior is a direct echo of the flare stars they are tied to. The mechanism is elegantly simple. Imagine a flashlight shining on a wall of fog. If you dim or brighten the flashlight, the illuminated patch of fog changes in response. In space, the flashlight is a variable star, often a young, erratic flare star, and the fog is a stationary cloud of dust surrounding it. As the star undergoes its dramatic brightening or dimming, the amount of light it casts onto the nearby dust cloud changes accordingly. The dust does not glow on its own, it merely reflects the star's light toward us. So when the star flares, the nebula brightens. When the star calms, the nebula fades. The most famous example connected to the Orion complex is NGC 2068, also called Messier 78. While not part of the main Orion Nebula, it is a brilliant reflection nebula in the same molecular cloud complex, lit by a small cluster of young stars. Historical observations suggest its brightness has fluctuated over the decades, likely driven by the variable output of its illuminating stars. This creates a celestial feedback loop we can watch in slow motion. A magnetic explosion on a star's surface, invisible to our eyes in detail, manifests as a visible brightening of an entire cloud of cosmic dust light years away. The nebula becomes a projection screen, amplifying and displaying the hidden turmoil of its stellar projector, a grand and silent testimony to the connectedness of this stellar nursery where every tantrum and every whisper leaves a mark on the cosmic canvas. Even the faintest embers in this stellar forge tell a story of cosmic limitation. Scattered among the thousands of brilliant stars in the Orion Nebula cluster are countless dim, reddish points of light, objects so cool and faint they barely register in visible light. These are the brown dwarfs, and they represent a profound failure. A brown dwarf is a celestial object that formed like a star, collapsing from a dense knot in a molecular cloud, but it never gathered enough mass to cross a critical threshold. To ignite sustained hydrogen fusion in its core, an object needs to be about 75 times the mass of Jupiter. Anything less massive than that simply cannot muster the internal pressure and temperature to become a true, self-sustaining star. Brown dwarfs occupy the awkward gap between the smallest stars and the largest planets. They may briefly fuse deuterium, a heavy isotope of hydrogen, or even lithium, but this fuel is scarce and burns out quickly. After that, they have no internal engine. They simply glow with the leftover heat of their violent formation. cooling and fading over billions of years like a forgotten ember. The James Webb Space Telescope, with its unparalleled infrared vision, has been finding them in staggering numbers throughout Orion. This suggests that for every successful star that lights up the nebula, there may be several of these failed stars, these shadowy giants that never quite made it. Their abundance forces astronomers to revise the initial mass function, the cosmic recipe that dictates how much material typically ends up in stars of different sizes. It appears the universe is far more prolific at making small, dim objects than we ever imagined. The existence of brown dwarfs blurs the line between star and planet, but deeper within the nebula's dusty folds, an even more unsettling discovery has emerged. Astronomers have detected faint, isolated blobs of warmth with no star to orbit. These are candidate free-floating planets, also called rogue planets. They are not gas giants circling a distant sun. They are solitary worlds, adrift in the eternal night of interstellar space. Some of these objects appear to have masses comparable to Jupiter or even Saturn, yet they float completely alone. Their discovery in a young nursery like Orion is a monumental challenge to our traditional stories of how planets are born. We have always assumed planets are a byproduct of star formation, coalescing from the disk of material left over after a star ignites. But if planets can be found wandering freely so soon after a star-forming event, it suggests alternative, more dramatic origins. One compelling theory is that these objects formed like stars in miniature. Tiny, ultra-dense knots in the turbulent cloud could have collapsed under their own gravity, directly forming planetary mass bodies without ever creating a central star. They would be brown dwarfs that failed even more spectacularly, landing squarely in the planetary weight class. Another, more violent possibility is that they were born the traditional way, around a star, but were violently ejected in the gravitational pinball of the dense cluster. A close encounter with another star could have flung a young Jupiter from its cradle, sending it on a lonely journey into the void. The evidence in Orion points to a population of these drifters, and if they are as common as early surveys suggest, the galaxy could be teeming with billions, even trillions of these dark, nomadic worlds. They are the ultimate orphans of the cosmos, born from chaos and destined to wander the darkness between the stars, forever untethered from the light and warmth of a sun. Hidden within the nebula's chaotic glow is a silent, guiding hand. To see it, astronomers must look at light in a way our eyes cannot, observing not just its color or brightness but its orientation. This property is called polarization, and it acts as a direct window into the magnetic fields woven through the cloud. Starlight begins its journey as an unruly mix of waves vibrating in every direction. But when that light scatters off the trillions of tiny, elongated dust grains floating in the nebula, something remarkable happens. If those dust grains are aligned like countless microscopic compass needles, they preferentially scatter light vibrating in one particular plane. The light that reaches us becomes polarized, carrying a subtle, organized signature of its last encounter with the dust, and what aligns the dust, the nebula's magnetic field. By meticulously mapping the polarization of starlight across Orion, scientists can trace the invisible lines of magnetic force that thread the entire molecular cloud. These fields are not random. They flow in sweeping arcs and follow distinct patterns, creating a cosmic scaffold that channels and constrains the turbulent gas. This magnetic skeleton is far from a passive bystander. It is an active participant in the nebula's architecture, resisting the chaotic pull of gravity and the push of stellar winds, imposing a subtle order on the chaos. It is this very interplay between magnetism and motion that sculpts the nebula's most fundamental feature, a structure so essential it is considered the bones of star formation itself. We see it etched across every deep image of Orion, a vast network of long, thin, rope-like strands known as filaments. These are not mere wisps of gas. They are dense rivers of molecular hydrogen and dust, each 1 light-years long but only a fraction of a light-year wide, weaving through the cloud like the threads of a colossal tapestry. Their formation is a direct consequence of that guiding magnetic field. As turbulence stirs the vast cloud, the magnetic fields help channel the flowing gas, funneling it along these preferred pathways. Gravity then takes over, pulling material down along the magnetic lines like beads on a string, condensing the gas into these incredibly long, thin structures. The filaments become the gravitational highways of the nursery, where these cosmic ropes intersect. Where the density soars to its highest point, gravity finds its strongest foothold. These intersections are the preferred sites for the birth of stars, especially the most massive ones. The entire Orion Nebula, with its brilliant clusters and dark lanes, is built upon this underlying filamentary web. It is a blueprint written in cold gas and dust, a pattern dictated by the invisible push and pull of magnetism, proving that even in a place of apparent chaos, there is an underlying architecture, a hidden order that guides the collapse of suns. Deep within the cold, dark filaments of the molecular cloud, a subtle chemical fingerprint is etched into the very fabric of the gas. It involves a heavier, rarer cousin of the common hydrogen atom, known as deuterium. When hydrogen and deuterium combine with other atoms to form molecules, the resulting compounds like hydrogen deuteride or deuterated ammonia become cosmic thermometers. The process that creates them, called deuterium fractionation, is exquisitely sensitive to temperature. In the profound chill of the pre-stellar cloud, only a few tens of degrees above absolute zero, chemical reactions favor the formation of molecules that contain deuterium over those with normal hydrogen. It is a small statistical preference, but over millions of years, it leaves a measurable mark. By measuring the ratio of deuterated molecules to their normal counterparts in different parts of Orion, astronomers can read the thermal history of the cloud. A high deuterium fraction is a frozen record, a sign that the gas has spent a very long time in extreme cold, undisturbed by the warming influence of newborn stars. As soon as a protostar ignites and begins to heat its surroundings, that delicate deuterium signature is quickly erased, resetting the chemical clock. So these rare molecules are more than just curiosities. They are forensic clues, allowing scientists to distinguish which parts of the nebula are truly primordial and untouched, and which have already been warmed by the hidden fires of stellar birth. In those same cold regions and in the warmer shocks near young stars, an astonishingly rich chemistry is at work. The simple ices that coat dust grains are being transformed into a zoo of complex organic molecules. Radio telescopes tuned to specific frequencies have identified a bewildering array of compounds swirling in the nebula's depths. We find methanol, essentially wood alcohol, floating in vast clouds. Formaldehyde, a molecule used in preservatives on Earth, is abundant. There are detections of methyl cyanide, vinyl alcohol, and even molecules like glycolaldehyde, a simple sugar. These are not just random chemicals, they are the direct precursors to amino acids and nucleobases, the organic building blocks for proteins and genetic material. Their presence in a violent stellar nursery is a profound revelation. It tells us that the fundamental ingredients for life are not rare or special. They appear to be a standard byproduct of star formation, forged in the cold darkness of molecular clouds and in the turbulent shocks unleashed by newborn suns. The universe seems to be preloaded with chemistry that leans toward complexity, scattering these organic Lego bricks wherever new stars and planets are being assembled. This means the raw materials for biology were likely present in our own solar system's birth cloud, delivered to the early Earth by comets and asteroids. When we look at the Orion Nebula, we are not just seeing a nursery for stars, we are witnessing a factory for life's potential, proving that the story of our origins is written in the chemistry of the cosmos. These delicate silhouettes of future solar systems are living on borrowed time. The same brilliant starlight that makes them visible is also boiling them away, a relentless process astronomers call photoevaporation. Picture a comet but in reverse. Instead of a tail streaming away as it approaches the sun, these proplyds grow their tails as they try to flee the radiation. The ultraviolet photons from the massive trapezium stars are so energetic they act like a cosmic blowtorch. When they strike the surface of a protoplanetary disk, they do not just bounce off. They heat the gas, primarily hydrogen, to temperatures of over 10,000 degrees. This superheated gas expands violently, achieving escape velocity, and streams off the disk in a wind that can reach speeds of several kilometers per second. The geometry creates the iconic shapes Hubble captured so perfectly. The side of the disk facing the trapezium stars gets the full brunt of the assault, its material boiling off first and forming a bright, curved ionization front, the glowing head of the tadpole. The material stripped away is then swept back by the pressure of starlight and the nebula's own stellar winds, forming the long, comet-like tail that stretches for billions of miles in the opposite direction. Each of those tails is a river of lost potential, gas and dust that will never coalesce into planets, moons, or comets. It is a breathtakingly beautiful form of cosmic destruction, where the cradle of new worlds is being dismantled by the very stars that lit it. This evaporation is not a gentle leak, it is a countdown. Astronomers have turned their observations into a grim calculation, determining the disk's survival timescale in such a hostile environment. By measuring the rate at which material is streaming off a proplyd's tail and estimating the total mass of the disk, they can essentially run the clock. The results are sobering. For a typical proplyd in the heart of the Orion Nebula, the entire gaseous component of the disk, the raw material needed to form giant planets like Jupiter and Saturn, could be completely stripped away in a mere 100,000 to 1 million years. In cosmic terms, that is the blink of an eye. To put that in perspective, our own solar system likely took between 10 and 50 million years to fully form its planetary architecture. This reveals a brutal bottleneck for planet formation in crowded stellar nurseries. Any world-building process here must be a frantic, high-stakes race. Dust grains must collide, stick, and grow from pebbles to planetesimals to full-fledged planetary cores at a breakneck pace, all before the gas reservoir vanishes. This timescale favors the rapid formation of giant planets through a process called core accretion, where a rocky core quickly gathers a massive gaseous envelope. If that core does not form fast enough, the gas will be gone, leaving behind only a system of rocky, terrestrial worlds with no gas giants. It also suggests that the final orbits of any planets that do form could be wildly different from those in our own solar system, sculpted in the chaotic final moments of the disk's evaporation. The survival of any planetary system in Orion is a testament to speed and perhaps a bit of luck, a reminder that the serene stability we enjoy in our own cosmic neighborhood is a privilege earned by escaping the furnace of our birth. The relentless winds and radiation from massive stars are not isolated events, they are collective forces that reshape the galaxy itself. When you gather dozens of these stellar titans together, as the Orion complex does, their combined power achieves something far grander than sculpting a single nebula. They create superbubbles. Imagine the cavity carved by the trapezium's winds, but on a scale 1,000 times larger. A superbubble is a titanic structure, often hundreds of light years across, blown into the interstellar medium by the concerted effort of an entire stellar association. The process begins with the hurricane-force stellar winds from all the massive stars in a region. For millions of years, these supersonic outflows slam into the surrounding gas, piling it up into a dense, expanding shell and hollowing out a vast interior. But the true architects of the superbubble's final form are the supernova. The most massive stars live fast and die young, ending their brief lives in cataclysmic explosions within a few million years of each other. Each supernova detonation delivers a staggering shockwave, an energy punch that further inflates the bubble and drives its shell outward at incredible speeds. In the Orion region, we are likely witnessing the early stages of this process. The collective winds from the trapezium and its many massive siblings are already excavating a significant cavity. In the coming few million years, as these stars reach the end of their lives, a coordinated series of supernovae will erupt, transforming this local cavity into a genuine superbubble that will eventually break out of the galactic disk, venting hot, enriched gas high above the plane of the Milky Way. This is not destruction, it is large-scale construction. The expanding shell of a superbubble sweeps up immense amounts of surrounding gas, compressing it into new, dense layers. And just as with the smaller bubbles around individual stars, this compression can trigger the collapse of new clouds, igniting the next wave of star formation in a wide ring around the bubble's edge. Star birth begets more star birth, but on a galactic scale. This cyclical process is part of a grander concept astronomers call galactic feedback. It is the mechanism by which star-forming regions like Orion regulate the ecosystem of the entire galaxy. The energy and momentum injected by stellar winds and supernova do several critical things. They heat the interstellar medium, preventing it from collapsing too easily and slowing down runaway star formation. They churn and mix the gas, stirring the heavy elements forged in stellar cores: carbon, oxygen, iron, silicon, back into the galactic reservoir. This chemical enrichment is vital, as each new generation of stars and planets forms from gas that is slightly richer in these metals than the last. Without this feedback, galaxies would quickly use up their cold gas in a single, frantic burst of star formation, leaving behind a stagnant, metal-poor system. Orion, as our closest grand stellar nursery, is the primary laboratory where we observe this feedback loop in action. We can measure the energy of the winds, map the structure of the cavities, and trace the spreading of enriched material. We are watching a living example of how the violent, short lives of the biggest stars govern the long-term evolution and chemical destiny of the entire Milky Way, proving that even in death, these giants sow the seeds for future generations of stars, planets, and perhaps life. The ultimate mystery of the Orion Nebula is not what we see, but how it all began. We have explored 50 of its strangest phenomena, from cosmic bullets to hidden giants, but every one of those wonders leads back to a single profound question. What was the spark? What colossal event first disturbed the quiet, cold expanse of the giant molecular cloud, tipping the balance so that gravity could begin its work of building stars here and not somewhere else? The brilliance we see today is the aftermath of a chain reaction, but the initial trigger remains hidden in deep time. Astronomers have several compelling theories, each pointing to a different kind of cosmic violence. One leading idea involves the grand architecture of our galaxy itself. The Milky Way is a spiral, and as it rotates, waves of compressed gas, spiral density waves sweep through its arms like cosmic traffic jams. It is possible that one of these waves passed through this region millions of years ago, squeezing the vast cloud and initiating its collapse. Another, more explosive theory points to a neighboring catastrophe. A massive star born in a previous generation far from the current nebula may have died in a supernova. The titanic shockwave from that ancient explosion could have raced through interstellar space for eons before slamming into the dormant Orion cloud, compressing it like a fist and seeding it with the heavy elements needed for future planets. Perhaps the truth is even more intricate, born from the cloud's own internal structure. Observations show the molecular cloud is not a simple blob but a tangled web of filaments. Where these cosmic ropes crossed and collided, their material may have piled up into knots of extraordinary density, creating the perfect seeds for gravitational collapse without any outside push at all. Each theory leaves a different fingerprint. A spiral density wave would have triggered star formation across a vast, organized front. A supernova shock would have left a shell-like remnant and a distinct chemical signature. Internal filament collisions would suggest a more localized, chaotic beginning. The evidence we gather today, from the motions of stars to the chemistry of the gas, is all part of a forensic investigation into an event that occurred millions of years before the first trapezium star flickered to life. We may never pinpoint the exact catalyst, but that is the essence of the mystery. It reminds us that every glorious structure in the cosmos, every nursery of light and life, begins with a disturbance in the dark, a single, silent note that starts a symphony. From that single, silent note in the dark, a symphony of 50 wonders unfolded. We have witnessed cosmic bullets screaming through the void, the ghostly green glow of shocked hydrogen, and stellar runaways flung from a gravitational brawl. We have seen natural lasers hidden in the dust, silhouette disks casting shadows of future worlds, and a hidden furnace of complex chemistry forging life's raw ingredients. Each phenomenon, from the photoevaporating proplyds to the explosive Orion fingers, reveals a fundamental truth. The Orion Nebula is not a serene painting. It is a dynamic, violent, and breathtakingly beautiful crucible. It is a place where creation and destruction are locked in an eternal dance, where the death of ancient stars seeds the birth of new ones, and where the very elements that build planets and us are hammered together in the heat of stellar forges. This journey through 50 of its strangest secrets has shown us that our own origins were written in a place just like this, a chaotic, radiant nursery where the universe practices both its artistry and its fury. The next time you find yourself under a clear winter sky, look for the 3 stars of Orion's belt. Just below them hangs his sword, and at its heart that faint, fuzzy patch. Now you know it is not a smudge. It is a city of suns being born, a chemical factory, a graveyard, and a promise. It is the great Orion Nebula, our closest window into the violent, creative heart of the cosmos. Which of its 50 strange phenomena fascinated you the most? Was it the stellar runaways, the hidden Becklen-Neugebauer object, or the eerie silence of the rogue planets? Let us know in the comments below, and if you want to keep exploring the universe's deepest mysteries, be sure to subscribe. Our journey through the cosmos has only just begun.